Hello. So we're going to dive into a special case, water, which can act as an acid or a base, just depending on what it's reacting with. So a substance that can either donate or accept a hydrogen ion, and remember we can also call that a proton, it's called an amphiprotic compound. So this is what we can call water. For example, if water is reacting with hydrochloric acid, which is clearly an acid, water will act as a base and it will take a hydrogen ion or proton from hydrochloric acid. And then we get our conjugate acid, the hydronium ion, and our conjugate base, the chloride ion. Now, if we mix water with something else, so let's say a base like NH2 minus, then water is actually going to act as the acid, and it's going to give a hydrogen ion to the base. And then we form our conjugate base, the hydroxide ion, and our conjugate acid, the ammonium molecule. So it really just depends on the relative acidity or basicity of what water's reacting with. So water tends to be neutral, right in the middle of acids and bases. So if we give water an acid, water relative to the acid will be basic. But if we mix water with a base, relative to the base, water is acidic. So it just depends on what we're mixing water with. Now, what's also interesting is water can react with itself. So since water can act as an acid or a base, we could have a situation where one water molecule is acting as a base and the other water molecule is acting as an acid. So the water molecule that's acting as an acid can give its hydrogen ion to the other water molecule, and we end up forming the hydronium ion, so the conjugate acid, and the hydroxide ion, the conjugate base. So our pairs, our conjugate pairs, the basic water molecule is forming the conjugate acid. The acidic water molecule is forming the conjugate base. So this is called the autoionization of water. And this occurs in every sample of water. So when you're drinking water, there's actually a very tiny amount of hydronium ion and hydroxide ion in your sample of water. But it's not very much, so you don't have to worry that you're actually drinking acids and bases. It's a really small amount. All right. So remember earlier, for acids and bases, we could write an equilibrium constant expression, and we can do the same thing for water. Now, this is actually given a specific name. This is called the ion product of water, or Kw. So this only includes the products. So Kw is equal to the concentration of hydrogen ions times the concentration of hydroxide ions. Now, sometimes we write this as the concentration of hydronium ions times the concentration of hydroxide ions. And that's, so remember H plus and H3O plus are somewhat equivalent to each other, so we can use them interchangeably. Now, notice that we didn't include the reactants in this expression. And our reactants, if we go back, were the two water molecules. So why didn't we include those? So we didn't include water because it's a pure liquid. And the concentration of water isn't going to change very much since we only produce a very small amount of the product. So that's why we don't include it. It's the concentration just isn't going to matter for water. Now, the value of Kw, this ion product of water, is very, very small. And that's because we do favor the reactants, which is H2O. So if we go back to this slide, we should actually have a double arrow here, an equilibrium arrow, because we're only producing a very small amount of the product, and the products can actually react to reform water. And I'm just going to make some room here. So the concentration of each product, once they're formed and we reach equilibrium, is 1 times 10 to the negative 7th moles per liter, or capital M. So notice how small that concentration is for each product. So again, when you're drinking a glass of water, there are hydronium ions and hydroxide ions in it, but they are such a small portion of that water. So that's really, really, really a tiny amount. So if we plug those values in for this ion product of water equation, that means we have 1 times 10 to the negative 7th times 1 times 10 to the negative 7th. And that gives us 1 times 10 to the negative 14th, which is what we saw before. So Kw will always equal 1 times 10 to the negative 14th. And I also have this on the next slide. So again, in a sample of pure water, the concentrations of the ions are equal to one another. And they're equal to 1 times 10 to the negative 7th moles per liter. And if we multiply those together, we get the ion product of water. Okay, so why do we care about that? So the reason we care is we can figure out whether something is acidic or basic by looking at the concentrations of hydrogen ions or hydroxide ions. So for acids, the concentration of hydrogen ions is going to be greater than 1 times 10 to the negative 7th. So remember earlier we said that water is neutral. So I'll put that up here. Water is neutral. And it always has a concentration of hydrogen ions equal to 1 times 10 to the negative 7th moles per liter. So if we were to look at an acidic solution, acids naturally produce hydrogen ions in solution. So they should have a higher concentration of H+. Now it's going to be somewhat the opposite for bases, right? So for bases, the concentration of the hydroxide ion will be greater than 1 times 10 to the negative 7th. So again, we said earlier that water is neutral, and its hydroxide ion concentration is also 1 times 10 to the negative 7th. So if a solution has a greater concentration than that of hydroxide ions, it should be basic. So let's look at an example. So hydrochloric acid, HCl, is a strong acid. We saw that earlier. And that means that all of the hydrochloric acid molecules completely ionize in solution. So remember, HCl completely ionizes in water to produce hydrogen ions and chloride ions. So there isn't a double arrow there. We just have a single forward arrow. We can't go backwards. So what is the hydrogen ion concentration and the hydroxide ion concentration if the solution has a concentration of 2 times 10 to the negative 3 moles per liter? Okay, so it doesn't look like we have hydroxide ions the way that we wrote this, right? But remember, water is present in solution. So let's see. If HCl completely ionizes in solution, that probably means that the H plus concentration is equal to the concentration of HCl. So that should be 2 times 10 to the negative 3 moles per liter. All right. So how do we figure out the concentration of OH minus? Well, we could use the ion product of water. We know that this should always equal 1 times 10 to the negative 14th. So we can actually apply this to other solutions as well. So let's plug in this value. Oops, my highlighter isn't working. There we go. So let's plug in this value for the concentration of H plus, and then we can solve for the concentration of OH minus. All right, so we've got 2 times 10 to the negative 3, and we'll multiply that by the concentration of OH minus, and that should always equal 1 times 10 to the negative 14th. All right, so now let's divide both sides by 2 times 10 to the negative 3rd. And that should give us the concentration of OH minus. So I'm just going to plug that into my calculator. Let's see. So I got a value of 5 times 10 to the negative 12, and that would be moles per liter, since that's the concentration unit we're using. All right, so again, even though earlier we said that the ion product of water was specifically for water, we can actually also use it for other solutions. And then we can figure out the concentration of either the hydronium ion or the hydrogen ion, they're the same thing, or the concentration of the hydroxide ion. So kind of handy. That's a handy equation. All right. So let's, in the next video, talk about the pH scale a little bit more. And this will be based on the ion product of water as well. So I will see you then.